No, I could just go Yammer. Yeah. Hello, everybody. So I'm Chris Brooks from the University of Michigan, and I'm going to speak to you today about a project we did looking at co-enrollment networks and the relationship to grades. And an important aspect of this is that this is actually, I want to give all the credit, none of the blame to my student, Josh Gardner, who did all the hard work and implementation of this work, and it's really his brainchild. So get that out first. So co-enrollments, we're motivated. Students, the social interaction between students can learn to lead in gains, and this is really the heart of social constructivism as a theory or a philosophy even. And social interaction at scale within higher education is difficult to measure. So these environments are both cooperative and competitive. Sometimes that depends on the course. And so we'll take a scaling of grades or curving of grades, as we call it, as one example. Interactions are also often poorly captured in the digital manner. And so sometimes it's really important to try and build models of students, and you don't have that deep, rich stream of data that you might expect from something like the LMS. So most research has been exploratory and focused on the explanatory potential of social network analysis within higher education, but not so much the predictive validity of these explanations. So the research question that I want to unpack with you today is, can we use co-enrollment networks in a predictive model for academic achievement? And I think that that's an important distinction between explanatory approaches. A little bit of background. There's actually a fair bit of literature cited in the paper, so I would encourage you to go there for more. But roommate relationships, as an example, have been well studied as far as co-enrollment and social network analysis, but there's been mixed results. So I actually like this quote from Winston and Zimmerman: strong students tend to increase peers' academic performance, and weak students tend to reduce it. Students of middling ability are usually more susceptible to peer influence than those at either end of the distribution. And that was really one of the big motivating quotes for us in actually considering co-enrollment networks and the relationship with GPA. McEwen and Soderberg dissent and say that there's no roommate peer effects on students' grade point averages. And actually, like I said, the paper has more on the details of the literature, but it's actually fraught with some people finding effects, some people not finding effects. In our approach, we focused on co-enrollment networks between students. We used a large data set, historical data set over 10 years from a single U.S. institution. Each semester of data, so we only looked at one semester at a time, had around 200,000, a little more than 200,000 enrollments in it. So it's a fairly significant size of data. We cleaned the data. Again, there's a whole bunch of information about how we did it in the paper, but actually ended up retaining most of the data. So very few things did we actually drop. One example is things that are pass-fail courses. So there's no GPA to predict in the end for students who are taking it in that method, or things where there was data that had a lot of cardinality in it. So our prediction task, what we were actually interested in doing, was predicting a student's GPA in a course within the letter grade, so an A, B, C, or D. And these are in most U.S. systems are characterized across, you could convert them to numbers, so 4, 3, 2, 1, with some exceptions, of course. So importantly, we can only know data, or we can only use data that we know at the beginning of the semester. We're interested in predicting somebody's grade, so we can't use the final grades of other students at the end of that semester to help us predict that grade. And that's an important issue here. Also, we wanted a robust model, so we trained on 9 semesters of data, but we're actually predicting on a full holdout set, full semester holdout set. So there's no cross-validation being used here for the reporting of these results. We're looking for a model that's got ecological validity. So I think the first finding that we had that was interesting was that co-enrollment networks actually look a lot like a lot of other social networks or networks in general, and that is they fit this power law model. So for example, in the co-enrollment network we created, we have nodes, we have edges. A node is an individual student, and they have a GPA, and each ed connects these students to somebody else, and there's around 22,000 nodes in a given network. But we see that the number of nodes that somebody is connected to is actually very similar to data from other kinds of networks. And so our co-enrollment network is on the left. You'll actually see the lines here are each of the semesters successively labeled on top of one another. And then this is a citation network from Newman, actually. And you can see that they're very similar. And so this is actually really useful to characterize the networks as being similar to other kinds of networks when it comes to creating features for feature engineering. One of the first things we did was we wanted to understand whether assortativity is useful. So the question we're trying to answer here is, do high-performing students co-enroll with other high-performing students? And you saw from the early quote that that was our motivation. And we actually saw that, yes, there was a strong correlation, or the assortivity coefficient is between -1 and 1, where 0 is neutral, and we can see that it's actually pretty replicable across all of the semesters of data that we're looking at it. So this suggests to us that birds of a feather do flock together with respect to GPA and co-enrollment, and that we expect that there will be more, that these networks will be useful for explaining GPA. One of the core aspects that we looked at is how do we actually create features for doing machine learning and building predictive models based off of networks. We built off the work of LAK'18, and so we actually take the network and we look at the link relationships, and we define a number of different functions to apply to those to create different features. So for instance, we have this one called the mean link, and this is just the mean GPA of students that one is co-enrolled with. Of course, this is their GPA, their cumulative GPA coming into the semester, because we don't have their final GPA for that course or for the end of the semester. Another one is this binary link. So for instance, we create some vector here, 1100, and this suggests that I'm co-enrolled with A students, I'm co-enrolled with B students, but I'm not co-enrolled with C students or D students. So we create these feature vectors using these different functions over the network. Count link is like binary link, but it's the absolute count of the number of students that I'm connected to in each of those different buckets of performance. And then proportion link is the same, but it just looks at the proportion of students in each of those buckets that I'm connected to. So there's kind of a philosophical question underpinning this, that what does it actually mean to be co-enrolled? What is the effect that we're expecting? So for instance, if Mary's enrolled in economics with Robert, what are we actually expecting Robert to do as far as influencing Mary and her performance, be it positive or negative? So we could consider only Robert's effect on Mary's economics grade. That is, that they worked together in an economics class, and thus he had a positive or negative effect on her grade that we can measure based on his GPA. So we built a network and a set of features like that, and we call those course link features, because it's really a single course that's making that impact. But also, Robert could just be a strong student or a weak student and bring up or down Mary's skills just in general. And so in that case, he's affecting all of Mary's grades. And so we created a set of those features as well, and we call these student link features. And we're trying to predict Mary's final grade in a given course. And so this is really telling us whether, or these two different methods are whether Robert has an impact on just that course, or Robert has an impact on all of Mary's courses. And so here's sort of an example. I'm just going to hit the highlights, but this student is an Econ 101 class. These are the kind of features that we create, and we create those because they're co-enrolled with student 2. They're co-enrolled with student 3 in a math class. They're co-enrolled with student 4 in a bio class. They're not enrolled at all with student 5. And so then we can create for the different buckets of grades, the count link, the binary link, proportion link, and so forth. So our next step was to do some actual explanatory modeling. And so do these network characteristics that we've created hold value just over cumulative GPA? And so we used least squares regression model, and network features actually explained 7 to 8% of the variance of themselves. And actually, when they were added to students' existing GPA, they added up to 3% extra. And this is exciting because this suggests that they're actually going to be of value beyond just your current GPA. So right now, current GPA is a great predictor of future GPA, and we've shown here that these network features, at least in an explanatory sense, can improve that. So we expect, I guess this is the punchline, we expect these features to be valuable in a predictive model. So our prediction tasks, armed with this knowledge, we revisit the prediction tasks. We train models on the first 9 semesters of the data, and we just lump those 9 semesters together. So the idea is our early warning system, we're not building one, but we're building underlying tools for one. Our early warning system wants to predict people's GPAs, and it uses all of this historical data about co-enrollments to help improve that prediction. We have a very basic kind of dumb model. Its kappa is 0. That is, it's just weighted by chance. So it predicts everybody gets an A and lots of people don't get an A, and that's our baseline of 0. Then we have another model, which is our GPA baseline, and we predict their cumulative GPA using only their previous GPA. So this is how good is GPA of a predictor of its own, and we get a kappa of about 0.21. So this is where a lot of papers would start with and then compare their values to that. But we actually have built lots of predictive models before, and we know we can do better than that. And so at Michigan, we have this Learning Analytics Data Architecture, LARC, and it's a flat file that describes a bunch of information coming out of our student information system. And I think we took 116 different elements from that, things like grades, credits, enrollments, honors programs, citizenship status, et cetera, and use these to improve the prediction. And I've got the URL there. I was going to jump out and show what LARC looks like, but there's just no time for that. But if you're interested in it, it's available. Not the data, but the description of the data is available. And what's important here is our best model that we build with this has a kappa of about 0.31. So that's really the value that we're setting ourselves up to beat. So how helpful are these co-enrollment models? Again, remember, LARC 0.31 over here. So we looked at these different features, mean link, binary link, count link, and proportion link, and we looked at them as far as the course. Remember, we have these 2 different models. Either Robert affects Mary's grade in one course, or he affects all of her grades, right? So it could be either of these. So we just throw them all into one big model here, and we get kappas of 0.29, 0.28. And so all of our co-enrollment models fail to outperform the base model. And so that kind of made me a sad panda. What if we just try the student link, though, the most liberal interpretation? Robert's a bad apple or a good apple, and it's influencing all of Mary's grades. And if we do that, we've actually simplified the model, and our kappa values using each one of these measures outperforms the LARC model. So now all of a sudden that's great, right? The co-enrollment values added to the LARC data outperform the LARC data alone. What's going on here? More data should make machine learning better, not worse, at the prediction task. And we hypothesize that it's the independence assumption between features is being too heavily influenced here, too heavily violated between the course and the student-linked models. So, can we do better? So we jumped in and we started to use a process called multiview modeling. And this is a way of ensembling models. And just as a quick overview, it means you build a model on pieces of the data where that piece of the data are independent. And then you take all of those models and you feed them into a bigger modeling process, which then learns relationships between the modeling, the first models that you built. So it's a hierarchical step. And this was actually really great for this approach because it allows us to increase accuracy of the model, but it retains some interpretability because we can look at how heavily weighted any of these individual models of. So again, our LARC model had a base performance of 0.314. The best model we've been able to build so far is 0.33. And then when we ensembled and we tried two different algorithms for this, a neural network and XGBoost, we got 0.34. So we're doing quite a bit better than the LARC model and a little bit better than our more simple models. So, takeaways from this talk. Co-enrollment explains some of the variance in student course grades. Co-enrollment can be used to improve accuracy of prediction if you're in a prediction task for course grades. The effect of or the relationship between co-enrollment and achievement is complex. And so we have all these multi-viewed models, and it's actually not very simple for you just to say, oh, Robert's going to influence all of Mary's grades. Sometimes yes, sometimes no, and the modeling is quite complex, and that's why multi-view modeling is great as a technique. And so I had a whole page of stats I can show you, but otherwise that's it. Yeah, so that's interesting. So on the first one, I don't think so. So we're actually predicting individual course grades, not overall GPA. The overall GPA is being used as an input. So you can still flunk courses as a senior, but there is I agree that the proficiency rises as well. On your second comment, though, I think you're bang on. I think with the first one, it would be interesting. We didn't decompose which courses or kinds of students that this is particularly powerful for. So this university that we looked at actually has a strong residential education program where people are living together. And there's also other networks we could have built on top of the co-enrollment networks, but actually co-enrollment networks, in this case, actually have some correlation to living networks because students are often, for instance, there's a women in STEM living learning community at this institution. So a lot of those students will be living together and co-enrolled in courses. And so these effects are quite muddy, actually. And so that's one of the reasons the literature, I think, is quite weak, or it's not weak, but it's contradictory. It reports both, that some are positive and some are negative as far as finding an effect. Right. Absolutely. So we just narrowed in on the very first of those, which is timetabled into the same thing, whether it's a tutorial or a course. Both tutorials and courses were counted as a course as far as the co-enrollments go. But I agree, adding all those measures is good. So we were just, and some of those measures are captured in LARC, but not a lot of the behavioral ones. For instance, did I interact with somebody in a group project? That's not captured in LARC. It's not captured in our data. It's definitely network data, definitely influential. I mean, it would be hard for me to conceive of it not being influential on student success patterns. Yeah, so this is just one sliver of a part of a predictive model, and I think there's much more, of course, to do. Yeah. Yeah, the temporal effect, and I think the gentleman here also spoke to that, and I think the temporal effect is really interesting, and we didn't look at it all. And there is something like, did Robert influence Mary in the first year, then influence her in the second year as well, or has Robert taken a course that Mary took before, and now they're co-enrolled in a different course, and maybe Mary's translating skills for Robert for the course that she's already taken? I mean, there's lots of scenarios, I think, here. And what's really interesting, I think, about the technique that we've taken is that we can apply them to those. We just have to rebuild our network. So in the paper, we have this sense of a network builder, which is an algorithm that builds the network. We have these two, the student or the course link builder. But I think that there's definitely some that involve a temporal aspect as well that would be important to check out, especially given how well this is already done in improving the quality of the model over just GPA, much better than just GPA, but also over our baseline realistic model, this LARC data set. Yeah. Yeah, this is definitely not a causal determination that we've made, right? That co-enrolling will influence your GPA, or does your GPA even influence who you're going to co-enroll with? And I think that it's actually quite true. So one of the schools that's got data in this data set actually grades on a grading scale not 0 to 4, but 0 to 4.25, which is bonkers, but they do it. And so there's like a super A, more than an A plus. And I think that that's, so, but we were able to just to throw that data right into this kind of model, make assumptions about it being independent, and still tweak out a little bit better performance. So I think that if we were able to get more information about courses, we could improve these models significantly. One way we've been trying to do that is actually through syllabi. And so trying to characterize courses based on their syllabi and trying to use automated methods. In part, we have 10 years of data on a big institution. So all of those syllabi, A, aren't available to us, and B, if they were, it would be an army to go through and actually categorize those courses.